In our previous lecture, we were looking at how things chemically bond now. We've talked about the electron structure of the atom and how that is going to be used as a tool to understand chemical bonding. And we noted that the most non-reactive elements are those called the noble gases, which are in the last column of the periodic table. And they have the unique structure that they have 8 electrons in their outermost energy position in the S and P level. So the S and P level of the highest quantum number is filled. Remember that we have 1 s orbital and 3 p orbitals, so we have 4 orbitals in the S and P, and each can hold 2. This octet, this 8 electron situation, is apparently a very energy stable condition for then elements, for atoms to achieve then in chemical bonding. And so we said that the driving force then in chemical bonding appears to be the tendency to achieve an octet of electrons, or in other words, to become like a noble gas, or we say noble gas-like electron structure. We further went on and said that we can look at individual electron dot pictures for each of the atoms to see how many valence electrons that it has. And this, of course, is determined by its location in the periodic chart. For instance, if I were to take element 15, phosphorus, and I locate it in the periodic table, I note that it is under the column number 5 in the P block. And remember that only S and P electrons are valence electrons. So elements in this column here, this family, nitrogen, phosphorus, arsenic, antimony, and bismuth, all have 5 valence electrons. They would have the 2s, and then for phosphorus we'd be 1, 2, 3 positions over 3p. So it has a S2p3 structure, so it has 5 valence electrons. And we can show those 5 valence electrons then by using an electron dot picture. So we would show 2 of them as paired and 3 singles to show the structure then for the phosphorus atom. And we said then that looking at this, we might suspect that what phosphorus would want to do is somehow gain 3 additional electrons. We'll just use X's. It doesn't mean that electrons are different, but to gain 3 electrons. And it can do this either by a give and take process, and if this occurs, if it's a give and take, in other words, phosphorus is going to take electrons, something needs to give electrons. This is referred to as ionic bonding. Because what happens when things give or take electrons is they no longer remain neutral atoms but become ions. And it's the ions that are then attracted to each other, opposite charged particles, that creates the bonding force. The bonding force in ionic bonding is electrostatic. That's what's holding the particles together. Opposite attraction forces. But also, it may be possible that the phosphorus or whatever atom it is that we're looking at may actually obtain this octet of electrons through a sharing process. And we'll be looking at the sharing process a little bit later today. So either by a give and take or by a sharing process, then an atom tries to achieve this octet, this noble gas-like electron structure. Let's focus here quickly, first of all, then on a few examples of some ionic bonding. And we'll start by looking at the reaction between cesium and bromine. Now, again, if we look at the periodic table and locate the two elements, we see that cesium, element number 55, is in the first column, indicating it has one valence electron. We go over here to bromine, and we see bromine is in this seventh column, so that it has 7 valence electrons. And so that's what we've shown up here in the drawing. Then cesium with 1 and bromine with 7. Now, cesium, in order to become like, then let's say radon would have to gain 7 more valence electrons. Not likely to occur. But if cesium were to lose 1 electron, it has 55. If it loses 1, it will have 54. And what has an electron structure with 54 electrons? Xenon has a structure of 54 electrons, meaning that cesium now becomes like xenon by giving up that electron. So we can show here we have, well, and then looking at bromine, I guess we should also mention, bromine has 7, and so in order for it to become like a noble gas, which would be krypton, it needs to gain 1 electron. So cesium donates its electron, gives it to the bromine. Now when this occurs, what we are going to produce then is we're going to produce a cesium with a +1 charge. So we're going to produce a positive ion, and we're going to produce a bromine with a -1 charge. And therefore, these two are now held together by opposite charges, by the electrostatic force. That's what we're talking about in ionic bonding. Electrostatic attraction is what's holding this together. Actually, then, in making up the compound, what we would find if we looked at a little solid chunk of cesium bromide, we would see something that looked like this. Cesium and then a bromine and then a cesium and then a bromine and then a bromine and a cesium and a bromine and a cesium and a cesium and a bromine, etc., as we go along, then making up the solid. But what I want to stress here is that there is no individual molecule. We can't say that these two belong together or that these two belong together. We don't know which two belong together, but we do know that we have a 1-to-1 combination. As a matter of fact, you see, we talked about the law of definite composition. The reason that cesium bromide, the compound involving cesium and bromine, will always be the chemical formula. As a matter of fact, we would just write it as CSBr. The reason that that chemical has the formula CSBr is that's the only way electronically those two can get together. It can't get together 2-to-1 or 3-to-1 or 2-to-2. It's only going to combine 1-to-1 because of the electron structure. That's why we look at the electron structure. It allows us then to understand why we have this law of definite composition, why there's only one way that these elements combine. It's not a haphazard thing. It is based on their electron structures. Now, a common compound that you're also familiar with is table salt, sodium chloride. Sodium chloride is an ionic compound in which sodium is given up an electron to a chlorine, and we make a plus and a minus ion, and they would make up a block of solid, then make up of little ions in that solid, that piece of salt that we're looking at. Again, sodium chloride. Sodium's in the first column, 1 electron. Chlorine in the 7th, 7 electrons. And so the only way sodium and chlorine can combine are 1-to-1 because of the electron structure. All right? Now, what type of compounds, or I should say what type of elements are involved in ionic bonding? Well, typically any of the metals on this side of the chart, in the 1A and the 2A especially, combining with any of the nonmetals, remember this is the dividing line here, any of the nonmetals, metals from this side and nonmetals are going to typically combine in an ionic fashion. So when I look at a chemical formula, I can make some prediction whether or not I would expect this to be an ionic bond, an ionic compound, or then a covalent or a sharing compound that we'll talk about in a little bit. Let's look at another example here. Let's take an element this time out of the second column under the 2A up there in the chart, and let's use strontium. And so strontium now has 2 valence electrons. Let's combine it with the nonmetal sulfur, and sulfur is over here under the 6th column, and so it would have then 6 valence electrons. And so how does strontium and sulfur get together? Well, again, if strontium were to give up its electron to the sulfur and give up another one to the sulfur, see, sulfur has only 6, so it can take on 2 more, we would end up with strontium now, which is atomic number 38 to start with. If it loses 2 electrons, it's going to have an electron structure with 36, and krypton is element number 36. So the strontium then, as it becomes a positive 2, will have a noble gas-like structure. So we can put down strontium 2 plus, lost 2 negative charges, and the sulfur S2 minus, and again, the only way strontium and sulfur can combine is 1 to 1 because of their valence electrons. Yes, question?
When drawing that, would you put dots there on the sulfur, or would you put X's to show that they transfer?
Well, when we do it, as far as the ions, we wouldn't put anything. The question was, do I put dots here or X's or whatever, and it doesn't make any difference. We're just using whatever manner we want to identify. If we wanted to show this, we could write SR, and then we could write S, which now would have the dots, and I can put an X for the ones that it gained, dots being the ones it had itself, and then X the one it's gained. But again, this is written this way, and again the chemical formula is SRS. It's the only chemical formula we can have for strontium sulfide. Now let's look at something that doesn't combine 1 to 1. Let's take another metal. This time we're going to take a metal from this 3rd column, so we're in the P block, but this is a metal, gallium. Gallium has 3 valence electrons. And let's react it with some iodine. Iodine has 7 valence electrons. Well, if we look at this, we can say, all right, I can see that gallium could give one of its electrons to an iodine. And if we did that, we would now produce then a Ga plus, but the Ga plus still has 2 electrons. And we would produce an I minus ion, which now has 8. So that I minus is already like a noble gas. It's not going to take on any additional electrons. So if the gallium, which still has 2 electrons, you notice the gallium hasn't become like a noble gas yet. If the gallium now still has 2 electrons, then it may be wanting to get rid of those. Well, we can go down here and we can show that the gallium plus ion produced in the first step now could give an electron to a second iodine atom, producing now a Ga2 plus, still has 1 electron left, it doesn't make any difference where we put it, plus another iodide ion. And that still hasn't achieved a noble gas-like structure. So finally, the gallium 2 plus gives up its 3rd electron and we form then now a Ga3 plus and another I minus ion. So when we get all done, this is what we have as the final, and this is what we had as the final. And so therefore, we can see that what we're going to end up with is GaI3. The way that gallium and iodine combine is that one gallium reacts with 3 iodines. That's the only chemical formula that we're going to have for that compound. So it doesn't always have to be a one-to-one giving process. In this case, we have then a 3-to-1 give and take process. But again, we can see why the chemical formula of gallium iodide is GaI3. Not GaI2, not Ga2I3, GaI3 is the only way gallium and iodine can get together. Now, gallium is not way over there where I mentioned, but gallium is a metal. Remember, anything below that jagged line is a metal. And so as a metal, it still has a tendency to want to give up electrons. The transition metals are a little less so. The metals in the D block, as we mentioned, are a little less able to give up electrons. And sometimes we see that they do. Sometimes we find that they actually do a sharing process. So we'll talk about that a little bit. All right? Any questions on this idea of the give and take then? Okay. Now let's turn to the sharing process, and the sharing process is referred to as covalent. And of course we know that the prefix co, like to cooperate, co-owners, whatever the case is, talks about a sharing of something. So covalent means a sharing of valence electrons. So if two things come together, for instance, and they can't become involved in a give and take process, then they might achieve a noble gas-like structure by a sharing process. All right? Now, if you recall, we talked about the fact that most of the elements are monoatomic. They exist as single atoms. But there are some elements at normal conditions, room conditions, that exist as molecules. Remember, hydrogen exists as H2. Nitrogen, oxygen, both exist as diatomic molecules, N2 and O2. And the halogens, fluorine, chlorine, bromine, iodine, and astatine, are all diatomic molecules in nature. Well, there must be some reason that they exist as those molecules. There must be something that energy stabilizes them to exist as that form, rather than being individual atoms. Well, let's look at hydrogen here for just a second. Hydrogen, atomic number 1, has 1 electron. And we'll have another hydrogen atom, and it has 1 electron. Now, if these two hydrogens were to come together, and they might then say, well, listen, I'm willing to share my electron with you if you're willing to share your electron with me. And in the process now, you see, this hydrogen over here would see 2 electrons around its nucleus. And this hydrogen over here would see 2 electrons around its nucleus. Now, what element has 2 electrons? Helium. So by sharing this electron pair, by each one donating 1 electron to form then a sharing process, then we have formed a noble gas-like electron structure once again. The hydrogen molecule, the atoms in the hydrogen molecule now have the same electron feeling as a helium does. They have a filled 1s orbital. Now we can show this in sort of a picture form as well here. Putting together here, now we're saying, all right, we had a hydrogen. It had one electron in the 1s. Remember, the 1s orbital is just a spherical space and the electron is in there and it can be anywhere. Matter of fact, it's just a probability plot of where it is. So that electron could be anywhere, and what we're going to show is that that electron now tends to move over in this area because it sees the other positive nucleus, and of course the other electron that was involved from the other hydrogen also is attracted, and so we end up with then the pair of electrons now located between the two hydrogens. So we have a pair of shared electrons involved here that accounts for then why these are held together. They're not held together because of electrostatic attraction. They're held together because of simultaneous attraction for a pair of shared electrons. That's a covalent bond. We usually show this when we write a structural formula as a dash. A dash in a formula indicates a pair of shared electrons. That's what that dash represents. Now, I said also that fluorine and chlorine and bromine as the halogen family all exist as diatomic molecules also. Before we look at their structure, we'll just look at the elements here. We have chlorine, diatomic, gas at room temperature. We have bromine, a reddish-brown liquid. We see a fair amount of gas above it, but its primary state at room temperature is a liquid. As a matter of fact, remember, bromine is the only nonmetal that is a liquid at room temperature, and mercury is the only metal that is a liquid at room temperature. And finally, we have iodine. It's a little hard to see in this particular picture, but actually the iodine now is some solid crystals located down here in the bottom of the flask. Iodine crystals almost look like metals, shiny little gray flakes. But there's enough molecules of iodine that escape from the solid that we see some of the iodine in the gaseous phase above it here, and iodine in the gaseous phase has a purple color to it. But the three then different halogens, chlorine a gas, bromine a liquid, and iodine a solid at room temperature. All are diatomic molecules, along with fluorine. We don't show fluorine here. It is just a colorless gas, and so it would look like an empty flask anyway, but it is in the gaseous state. Well, let's see if we can understand then what it is that allows fluorine now, which would also represent chlorine, bromine, and iodine because they all have exactly the same electron structure. How do they get together to form diatomic molecules? Well, I've drawn here the picture of each of the fluorine atoms. I just put them in slightly different color here so that we see then what is occurring. Each fluorine, chlorine, bromine, iodine, each halogen has 7 valence electrons. So we see here now that we have fluorine with pair, and a single for its 7, the other fluorine with its 7. Each one would like to have 8. So again, we run into the situation where we can say, this fluorine says, I'll share this electron with you. This fluorine says, all right, I'll share this electron with you. We now have a pair of shared electrons in there. If we then put a circle around here, we see that we have, in fact, 8 electrons now available to that fluorine nucleus. And over here, this one also has 8 electrons around it, so each has a noble gas-like structure. So we're sharing a pair of electrons. To show the molecule, then we write it in this fashion with a dash in between. Sometimes in structural formulas we merely write the symbol, so we could write it like this. Chemically, in an equation, we would write it like that. It all means the same thing. But we will be interested in these other electrons as well as we get into talking about molecular geometry, and that is that these electrons here are referred to as non-bonding electrons. Quite obviously, they're not involved in the sharing process, so they're called non-bonding electrons. And non-bonding electrons, as I say, will be important to us when we consider molecular geometry. Now, from a physical standpoint, let's see what this looks like. Now, remember, we have 4 valence orbitals, s and 3 p's. And remember, the p's are always slightly higher in energy than the s. So if we're putting electrons in now, we're going to put a pair into the s, and then a pair into the p, and a pair into a p, and 1 in the other p. So one of the p orbitals has only a single electron in it. So if we look at this, then we're saying here is now the fluorine atom. 2p orbital. Remember, an orbital, a p orbital, is a figure 8 shaped structure. That double lobe right there contains just 1 electron. It could be on either side of the nucleus. But as 2 fluorine atoms approach each other, then the electron from this one might be on that side, and the electron in this one might be on that side. It has equal probability when the atoms are all by themselves of being on either side. But now as these positive nuclei come together, these electrons tend to move in between, so that this one now becomes attracted to that nucleus, and this one becomes attracted to that nucleus. When we get all done now, we have a pair of electrons sitting here in between the 2 fluorines. And that's what then accounts for the chemical bond that we show as the dash. That's that pair of shared electrons between the 2. So, as I say, because they're in the same family, of course, this explains the behavior of all of those: fluorine, chlorine, bromine, iodine, and astatine. But there are 2 other diatomic molecules: oxygen and nitrogen. Let's look at oxygen first of all. Now, oxygen is in the 6th column, telling us it has 6 valence electrons. So, if we were to bring 2 oxygens together, and again I've colored these merely so that we can kind of follow what's going on. This oxygen has 6 valence electrons, this one has 6 valence electrons. To be like a noble gas, they have to each have an octet, or 8. Well, again, this oxygen up here says, I'll share this electron with you and this one with you, provided that you'll share this electron with me and this one with me. And if we do that, then of course we're going to end up with the 2 oxygens now, with actually 4 electrons being shared between the 2, and then of course each one would still have its own non-bonding electrons that weren't shared. These 2 pair here and these 2 pair here now are not being shared. Those are the non-bonding electrons. Now, a chemical bond represents a pair of shared electrons. In this case, we have 2 pairs of shared electrons, and so we show this then by using a double dash, which is called a double bond, which implies that 2 pairs of electrons. Each dash represents a pair of shared electrons. And so if we look at this oxygen here now, you see it has around it 2, 4, 6, 8 electrons. if we look at this oxygen here, it has 2, 4, 6, 8 electrons. Both see 8 electrons around the nucleus, and it's become like a noble gas. Finally, nitrogen, and we've noticed nitrogen on the periodic table is in the 5th column, meaning that it has 5 valence electrons. Obviously, to get an octet, it has to gain 3. Well, if we look at the electron arrangement of the nitrogen, again, we can show that it would have to have a pair and 3 singles in its 5 electron structure, and the other nitrogen would have a pair and 3 singles. So this time, the nitrogens then are going to say, all right, I'll donate this one, you donate one. I'll donate this one, you donate one. I'll donate another one, you donate another one. And so we end up then with nitrogen now with 1, 2, 3 pairs of electrons that the 2 nitrogens are sharing. And then, of course, each nitrogen still has this pair of electrons, non-bonding pair of electrons that weren't shared. But if we look at this nitrogen here, it now sees 8 electrons. If we look at this nitrogen here, it is now seeing 8 electrons. This time we have shared 3 pairs of electrons, and we then show this in the formula by 3 dashes called a triple bond. 3 pairs of electrons are being shared. Now, there are only a few elements that really can share more than 1 pair of electrons. Carbon can share a single pair, 2 pair, or 3 pair. Nitrogen can share a single, 2 pair, or 3 pair. These are the only 2 elements under normal chemical reaction conditions that can share 3 electron pair. Only carbon and nitrogen can form a triple bond. Okay? Now, both carbon and nitrogen can form double bonds, but there are a few other things that can form double bonds as well. Oxygen, sulfur, phosphorus, silicon, as 4 other elements that can form double bonds, share 2 pair of electrons. The rest of the elements, when we're doing covalent structures, are only going to share a single pair of electrons. Now, it may share a single pair of electrons with 3 different things, but it will only share 1 pair between each individual atom in the molecule. So there are only a few that we have to worry about that are involved, then these 6 right here, that are involved in what we call multiple bonds, which means, of course, extra pairs of shared electrons. Now, one of the areas of chemistry that we have been talking about, of course, is the organic chemistry. And if we look up there, I just mentioned that carbon has the ability to form single, double, and triple bonds. And so we'll find that frequently in organic compounds, carbon-based chemistry, that we do have this multiple bonding process. For instance, one that we've already looked at, we looked at the carboxylic acids. And we drew this as the general structure of the carboxylic acid. We didn't have the little X's on there before. But the structure showed us that the carbon had 2 bonds to the oxygen. That means that the carbon and the oxygen are sharing 2 pairs of electrons between the 2. Now, one other thing that we have said before, carbon can only form 4 bonds. That is because, of course, we only have 4 valence orbitals. When we fill those, we can't then share anything more. So carbon forms only 4 bonds. In this case, we show that it's sharing a pair of electrons with whatever this group is out here, a pair of electrons with this oxygen, and 2 pairs of electrons with this oxygen. So we see the carbon has, in fact, 4 covalent bonds. And then we see this oxygen, of course, is sharing one pair with the carbon, one pair with the hydrogen. So as far as the oxygen is concerned, it has 8 electrons. As far as this carbon is concerned, it has 8 electrons, 2, 4, 6, 8. This oxygen has 8 electrons, 2, 4, and then 4 non-bonding, 8 electrons. The hydrogen has 2 electrons, and of course that's all hydrogen wants because that makes it like helium. So everything in that carboxylic acid has satisfied then the octet through either a single bond, a single sharing process, or a double sharing process. Now there is a group of hydrocarbons. We've talked about hydrocarbons before. Hydrocarbons are those organic compounds containing only carbon and hydrogen. The first ones we talked about we called saturated hydrocarbons. Now we're going to look at the group that we call unsaturated. Unsaturated hydrocarbons mean that they have at least one carbon-carbon double or triple bond in the structure. Hydrocarbons that contain only carbon-carbon single bonds are called saturated hydrocarbons. We already looked at those several times. Let's just take the first group of these. We've already talked about the 2-carbon saturated. This is the saturated one. This is the one that we talked about before. Okay, this was the, as I say, saturated. And we called it ethane. The ending ANE indicated only carbon-carbon single bonds. If I put a double bond between the carbons, it's still like an ethane, but we change the ending and the name to ENE. And that ending, ENE, when I see it in the name of an organic compound, implies a carbon-carbon double bond in the structure. And finally, when we put the 2 carbons together, but we share 3 pairs of electrons, and if we looked at these, in every case the carbon still is achieving an octet, we call this ethyne structure. The YNE, when I see that in an organic compound name, indicates the presence of a carbon-carbon triple bond, 3 pairs of shared electrons. Now, this continues on, just like we did. We had ethane, propane, butane, pentane, hexane, and so on. We have the same type of thing that would occur as we went on to the others. If we go to the 3-carbon saturated, it's propane. The 3-carbon with a double bond in is propene. The 3-carbon with a triple bond in it, propyne. And so we can continue on using that nomenclature system. But if you recall, in the saturated hydrocarbons, we did see that we can have the same chemical formula, but put it together in more than one way. And these we called isomers. And so yes, we have isomers when we're involving unsaturated hydrocarbons. As a matter of fact, we can have more isomers when we have unsaturated hydrocarbons, because not only can we attach little side groups like we did, put in a CH3 group, a methyl group, or a C2H5 group, an ethyl group, and hang at different places. Not only can we do that, but we can move the double bond or triple bond around, and that makes a new compound. Now, don't bother writing any of these down. You're not responsible for this, but I just wanted to show you here quickly what we mean by the isomers involving the unsaturated. These are all 5-carbon structures. 5 in a row would be pentane. But if we have the double bond, it's pentene. But there are 2 ways we can put the double bond. We can put it starting on the 1st carbon, or we could start it on the 2nd carbon, and those are 2 unique molecules. The way we identify the difference, notice the base name is still pent, meaning 5. Both are ene, meaning a double bond, but we put the number 1 or 2 in front with a dash to indicate where that double bond is starting. Well, not only then, down here in the next isomer, we're going to put 4 in a row, so we're going to make it a butene, and then we're going to hang a group underneath, the methyl group. So we call it 2-methyl. The methyl group is on the second carbon, and the base compound is 1-butene. It's a 4-carbon with a double bond starting on number 1. Okay? And then this one, the methyl group is still on the number 2, but now the double bond has been moved to number 2, so we have 2-methyl 2-butene. Okay. Again, don't worry about the naming or drawing of these, but I just wanted to show. And here then, of course, we could have the double bond here and move the methyl group, and we have another new molecule. So you see that we can really get a lot of isomers once we begin looking at unsaturated hydrocarbons. I drew this one here just to show that we could draw this as a propene with 2 methyl groups, but I put an X through it. And why did I put an X through it? Carbon has 5 bonds. At center carbon here, we have 1, 2, 3, 4, 5 electron pairs being shared, which is 10, which is not an octet, which doesn't make sense that it would be energy stable. And so that isomer, even though we could draw it, doesn't fit that carbon forms only 4 bonds total. All right? Now, what if we have more than 1 double bond in a molecule? Well, we call those then polyunsaturated. And certainly, that's a term that you've heard. If you've heard any commercials on margarine and butters and things like this and cooking oils, one of the key words in the advertisement is polyunsaturated. If they can say that, if they can say that the oil is polyunsaturated, that means that it doesn't really mean. That is to imply that it is healthy for us. Polyunsaturated oils contain then molecules that have double bonds in them, which supposedly is easier for us to digest and less likely to lead to a cholesterol buildup. And so when we're looking at different types of cooking materials, animal oils usually are saturated oils, meaning they have all carbon-carbon single bonds. Oils from various grains like safflower, soybean, corn, those are polyunsaturated oils. Therefore, if we cook with those and we eat some of them from the cooking process, they should be more easily digested and less likely to lead to cholesterol. All right, there's still a lot of debate on the total effect of both. But this would represent now a polyunsaturated molecule. Notice that I have a triple bond and a double and 2 double bonds in there. So it has 2 or more double or triple bonds. It's called polyunsaturated. Now, one other thing that we talked about in the saturated or the single bond were the cyclic compounds. And we can have cyclic compounds that involve multiple bonds as well. That was cyclobutane, 4 carbons hooked together in a loop. If we hook 4 carbons together in a loop but put 1 double bond in, it becomes cyclobutene, and the ENE is the clue there as to the name and the double bond. We can also have polyunsaturated cyclohydrocarbons. If we look at this one here, this is 6 carbons with alternating single, double, single, double, single, double bonds, 6 carbons, okay? So the base name would be cyclohexene, ENE to show double bonds, but there are 3 of them in there. So it would have to be cyclohexatriene to show 3 double bonds. And as a matter of fact, we'd have to tell where they were. In other words, that they weren't each adjacent to each other. So the actual naming of this is 1,3,5-cyclohexatriene. Don't worry about that. Okay. This is usually drawn in this form here. So if you see this in a structure, if you see that in a chemical formula, that means this structure over here, 1,3,5-cyclohexatriene, which has a more common name in organic chemistry of benzene. So we can draw it this way and show all the bonds, or we can just draw it this way. That circle in there means alternating double bonds, and that's also benzene. We'll talk some about substituted benzene compounds in a little later chapter. But polyunsaturated cyclohydrocarbons. Now, one last topic to touch on today. When two atoms come together, what is going to determine whether or not they share or give and take electrons? This is called electronegativity. Electronegativity is the attraction for an atom for the pair of shared electrons. Basically, whether something is ionic or covalent at the end. Everything comes together initially in a sharing of electron process. But sometimes the sharing becomes so unequal that one of them gets the electron all of the time, and when that happens, we're ionic. When one of them neither gets the electron any more than the other, we're talking about covalent. For instance, when two hydrogens come together, we would expect that each hydrogen should equally share that pair of electrons. As a matter of fact, we refer to that as pure covalent. That means equal sharing has occurred. When two oxygens come together to make diatomic oxygen, we would consider that pure covalent. But what happens if we bring together a hydrogen and a chlorine, for instance? When we bring together a hydrogen and a chlorine, we do form a bond here. But if we look at this electronegativity, the attraction for both of these to that pair of electrons, we find that they're not the same. Hydrogen has an attraction of 2.1. That's its electronegativity value. Chlorine has an electronegativity of 3.0. It is stronger attracting those electrons than the hydrogen. So the electrons are going to spend a little bit more time with the chlorine than they are with the hydrogen. This unequal sharing is referred to as then polar covalent. Equal sharing was pure covalent. Unequal sharing is polar covalent. Now, the term polar comes from the fact that if we were to show this molecule and this pair of electrons is actually spending more time over here by the chlorine, it means that this end of the molecule is going to be slightly negative. And this end of the molecule is going to be slightly positive, or this end of the bond, I should say, will be slightly positive. So we have a slightly positive and a slightly negative end, and so we're talking about polar covalent. But when I put sodium and chlorine together, that pair of electrons that we had between, sodium only has an attraction of about 0.9, chlorine 3.0. It's definitely unequal. But it's so unequal that we actually consider that the electron spends all of its time with the chlorine. As a matter of fact, the guideline that we use is if the electronegativity difference, we'll call it delta EL, if the difference in the electronegativity of the two atoms is greater than 1.6, we say that it is ionic in its bonding. And in our next lecture then, we'll take a look at the electronegativity table and predict some polar, nonpolar bonds, and go on and talk about molecular geometry and polar molecules.